Implicit differentiation is a very tool when solving for y is a challenge. For example, to solve for y here, y is going to be the square root of 1 minus x. That's only true for x equal to 1. But what if I have something like y to the fifth plus y squared is x cubed plus 3? I can't solve this one explicitly at all. So we're going to use implicit differentiation when you cannot solve it explicitly, or when it's just a difficult, or obviously when I tell you to. Now here are the steps. Differentiate both sides with respect to x. Collect all of the dy dx terms on the left, move everything else to the right, factor out dy dx, and solve for dx. Let me go back to the first one. Clearly, if I do dx of y, I will probably call that y prime. If I do dx of y squared, that's 2y prime. This right here is the first derivative. Don't put a 1 there. So that if I do d dx of y to any power, that's going to be n, y to the n minus 1 times y prime. You have the generalized power rule here. Now let's try implicit differentiation on this equation. If I do d dx, and I'm going to write this particular step out, you don't have to, y cubed plus y squared minus 5y minus squared equals d dx of negative 4. All right, so this becomes 3y squared y prime plus 2y prime. I can draw arrows down here if that'll help you. Minus 5 times y prime minus 2x. And you see there's no x prime because I'm taking the derivative with x. And the derivative of constant is, of course, 0. So the next thing I'm going to do is collect all of my y primes on one side, everything else to the other. And so this is 3y squared y prime plus 2y prime minus 5y prime is equal to 2x. The next step, which I'm going to red, is you factor out your y primes. And yes, you could have combined these two steps. I'm just being very meticulous here. All I'm doing is factoring out y prime, and that's equal to 2x. And the last step is to get y prime by itself. So the 2x divided by 3y squared plus 2y minus 5. Now I cannot solve explicitly. A lot of times I'll be able to plug back in, but I can't in this case. Now sometimes I want to find the second derivative. If I want the second derivative, then clearly I have to do the first. So the first derivative is 2x plus 2y prime is equal to 0. Now, for reasons that are going to become obvious in a minute, I'm going to solve this for y prime. So 2y prime is minus 2x. So y is minus x over y. The next thing you're going to do is take the second derivative, and you're going to want to go back to this right here. So let me rewrite it as x plus y prime equals 0. I simplified it. So now I'm going to take the second derivative of this. So this is 1 plus, now I have to use the product rule. So this is going to be y prime times y prime plus y times y double prime, and still it equals 0. So looking for the second derivative. So let me solve this for the second derivative. Y double prime is minus 1 plus y prime squared. All right, because there are two of those. And I've got that negative sign here. So y double prime is minus 1 plus y prime squared all over y. Now I want it in terms of x, and so I need to come back up here and plug in y prime equals minus x over y. And when I do that, actually I should have put y double prime here, shouldn't I? Sorry about that. And when I do that, I'm going to get y double prime is equal to minus 1 plus y prime is negative x over y squared, whole thing over y. Now, can I simplify this? The answer is, of course. All right, this becomes, let me switch colors again. Let's see, minus y squared plus x squared over y cubed. Now notice I can simplify this just a little bit more. I've got this negative sign outside of the parentheses, so this is negative x squared y squared over y cubed. But what was x squared plus y squared? It was 25. Sometimes pretty tricky. So this is negative 25 divided by y cubed. So this is the second derivative of my circle at this second derivative of my circle.